Welcome back, ladies and gentlemen. We're moving on to Chapter 9, Section 1. Day 1 is going to be sequences here. We're going to find the term or terms of a sequence, depending on the question, basically. We're going to write an expression for the nth term of a sequence. Well, nth just means the first, second, third, fourth, fifth, etc. And simplify expressions involving factorials. Okay, first of all, by definition, a sequence is simply a list of terms. So it could be something like 1, 1, 2, 3, 5, 8, and so on, which maybe you recognize that as a very famous sequence called the Fibonacci sequence. Actually, it was developed by an Italian mathematician trying to explore something about rabbit populations, and he came upon that, and it's got all kinds of great little other uses. But anyway, another possible one is, let's say, 17, about pi, square root of 2, let's go with e, and then 5, and then we could keep going forever. But if you're trying to figure out a pattern for that, there is none, because I was simply doing that randomly. Okay, so any old list of terms, there could be a pattern, there could be some kind of a rule to it, or it could be just whatever. That's what a sequence is. However, for this lesson, we're going to use sequences that are generated using functions, as it says here, quite honestly, because the random ones aren't really much good for much. Ones that have patterns of some sort are usually a little more interesting and meaningful. Alright, now if I need to write various terms of sequences, we're going to assume that the n begins with 1 when we're doing what we're doing here, but just for whatever term of the sequence we want, for instance, we could write the first 5 terms of this. Okay, now first of all, there's a little notation that may look a little bit weird, that a sub n is just a fancy notation for the nth term, and again, in case that's not quite clear, if I write a sub 1, what that means is the first term. If I write a sub 2, that means the second, and I'm guessing you probably got the idea by now. Alright, so first 5 terms again. N begins with 1 is going to be the rule that we're going with. Depending on what you're doing, you could actually start with a different n value. Sometimes n equals 0 is a good starting value, but for the sake of the way the book did things, therefore the way I'm going to do things is we're going to assume n begins with 1 just so we're kind of all on the same page. So basically, a sub 1, okay, and then you just basically take this little formula here, and anywhere you see an n, plug in a 1. I'm sure that wasn't too much of a shock. So, of course, 6 times 1 is 6, minus 7 is negative 1. Okay, move on to a sub 2, plug in a 2, and we got 12 minus 7, which is simply 5. And I trust you don't need to see the rest of the work for this, but as I keep going, I would get myself an 11 as I plugged in the fourth one. If I plug a 4 in for n, I would eventually get myself to a 17, and then a sub 5 would get me to a 23, and if you're clever, you might have noticed a little pattern with these numbers that would have made even a little bit of this calculation not very important to do. But anyway, that's how you do, just plug it in and you get what you get. Okay, you might want to be able to write expressions for the terms of a sequence, because quite honestly, if you've got a list of numbers here, and if I can come up with a formula, that'd be very handy, especially if, let's say, I needed the 50th one in this sequence. Okay, well, I could go 4, 8, 16, 32, and if I figured out the pattern, I could keep doing it for a while, but again, if I needed the 50th one, it would take quite a while to get there. So if I had a little formula, I could do it a little quicker. So here we go. Let's kind of figure this guy out. Alright, so I started at 4, go to 8, go to 16, etc. So my gut reaction normally is to think, okay, maybe it's addition. So if I start at 4 and go plus 4 and get to 8, well, that sounds good. If I go plus 4 again, I get to 16. Okay, so it's not simply just adding a number. Okay, so I got to try something else. Well, 4 to get to 8, well, maybe that's like times 2. Okay, so 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32. Hey, I've got myself a pattern, because basically from here to here, I'm just going times 2, from here it's times 2, etc. So basically I figured out how to get from one number to the other. Okay, so then it's just a matter of writing that in an a sub n equals expression sort of format. And I confess there is more than one way to do this, and more than one right answer, technically. Okay, so basically what I like to do is do a sub n, and then I kind of like to go with whatever the first guy is, and then kind of figure out what I have to do to modify it, and go from there. So here's one answer that would work. Okay, so a sub n, again, my first guy is a 4, so I'll just basically throw the 4 down there. Okay, and then what I'm doing from there is I'm modifying it by multiplying by 2. Now, you do have to be careful here, because I'm doing 4 times 2 now. Now, here's the interesting thing. Alright, if I take 4 times 2, I certainly don't get 4, I get 8. Okay, so I do want to multiply by 2 repeatedly, but what I need to do is not multiply by 2 on the first one. So basically, if I just take this guy minus 1, okay, notice now 1 minus 1, remember I'm starting with n equals 1 all the time. if I do n minus 1, that's basically a 0, and 2 to the 0 is 1. So on my first term, I do actually still get the 4, because 2 to the 1 minus 1 would be, well, 1. So I still get the 4, and then when I do n equals 2, I do 2 minus 1 here, and that gives me a 1 exponent overall, and 4 times 2 does give me the 8, etc. So basically here is one possible final answer. But there might be different ways to do this. For instance, hey, 4 is simply 2 times 2. So if I kind of think of this as 2 times 2 times 2 to the n minus 1, well, I can get really clever and call that a 2 to the first times n minus 1, add these two guys together, and that just becomes 2 to the n, and then I have this other 2 that's left over. So I could write that as 2 times 2 to the n. And that would still exactly generate that same list. Again, imagine n equals 1. Well, 2 to the first is 2 times 2 gives me the 4. 2 to the second is 4 times that 2 gives me 8, which again is exactly what I have, and you could test that with the rest of them. But again, you might notice those two 2's are very similar, so hey, doing a similar thing as I just did right here, what if I just left that 2 in the front as 2 to the first, and then still had that 2 to the n and put them together? So a to the n equals 2 to the n plus 1. Alright. And I confess I don't know if one of those is necessarily better than the other, but just the point being that, hey, I can get this list and I can do it using 3 different versions of the same formula, and quite honestly I could probably play around and get a little more crazy if I wanted to, but there are 3, I think, very good answers right there. Alright, moving to the second one right here. This one might look a little more complicated, but it's actually kind of easier. But basically here's my advice. If you have a fraction, okay, basically what I want you to do is split the top and the bottom and just think of them as 2 separate ones, and basically just get those 2 answers and stack them together. Alright, so basically here we go. So a sub n equals, and again, big fraction bar, and I'll just come up with an expression for the bottom, expression for the top, and that'll be my answer. Okay, so now looking at the bottom, we've just got 2, 3, 4, 5, 6, 7. That's a pretty simple pattern. So I'm just starting with sort of an n and counting up by 1. But again, I want to get to 2, so really, if I just simply add 1 onto it, okay, again, if I stick in 1 first, well, I got a 2. If I stick in 2, I get a 3, so it does give me the exact numbers in the order that I want them. So, pretty simple denominator. Okay, now my numerator bounces between -1 and +1. Okay, well, the way to pull off something like that, okay, is simply take a -1, and then we just need to take it to the power, but all you have to do is make sure that you pay attention to, generating the power even versus odd exponents. Okay, so I'm just going to throw an n up there to start with. Okay, now again, I'm starting with n equals 1. If I use a 1 first, I have -1 to the first, which is -1, but looking up here, I do have a -1, so I feel pretty good about that. Okay, again, if I stick in a 2, okay, notice -1 squared gives me a +1, and that's what I have. And -1 to the third gives me a -1, so again, that's what I have. So, hey, that feels good. Okay, if I needed to start with a positive, all I had to do is take this n and put a little +1 on it or a -1 on it, and that would kind of change the negative to a positive, and I would have what I wanted anyway. But anyway, there you go. Hopefully I didn't babble too long on that. But there's that one. Alright, I want to show this next problem here, mostly so I can show the following problem, but here we go. Okay, I've got -1 to 2, and then 2 to 5, and 5 to 8. Okay, now hopefully it's not real tough to figure out that this guy is simply adding 3 each time. Okay, so now what I basically want to demonstrate with this is that if I, again, basically do that, think of this as +3 to get to there, then +3 to get to there, etc. Okay, basically, notice here what we call the first difference, okay, which is basically what we get by subtracting these guys the first time, and that'll make more sense when I do the next example. But by subtracting these guys the first time, I get the same thing the whole time. So, since the first difference is constant, that lets me know that basically what I have is a linear sort of pattern. Okay, so right now I know I'm linear, so I know I'm going to never use any exponents here, because again, linear, y equals mx plus b sort of approach. So, okay, and a sub n is playing the place of my y, and then I basically need to start at -1 and count up. Now again, my basic idea is I need to start off with my kind of starting guy. So again, my starting guy is -1, but I need to add on to that 3. Okay, but notice again, the first time I don't actually add the 3. So I actually add 3, 1 less than the term that I'm on. Because again, if I'm on term 1 here, term 2 here, term 3 here, etc. Okay, for the first guy, I don't add the 3 at all. To get to the second guy, add him once. The third guy, add him twice, etc. Again, notice I'm always one less. So basically that's what that does. And here I think this would be nice to clean this guy up. So -1 plus 3n minus 3, doing a little combining like terms, my nth term ends up to be a nice clean 3n minus 4. And again, a good idea to do is to double check this. If I put a 1 in there, 3 times 1 is 3, minus 4 gives me -1. Yep, feeling good. 3 times 2 is 6, 6 minus 2 is, 6 minus 4 is 2, so I'm feeling pretty good. I am generating the terms that I'm supposed to generate with this expression. So there we go. Okay, now again, I did the last one, so I could do this one and show how this guy comes together. I've got 7, 10, 15, etc. Now again, you might look at this and say, okay, well, plus 3, and then, ooh, that's not plus 3. Uh-oh, got problems. Alright, so here's at least one approach that sometimes works, so I want to give you at least this tool for your mathematical toolbox. Okay, so again, from 7 to 10, again, you might have thought, okay, well, that's plus 3. Alright, cool. 10 to 15, that's plus 5. Okay, right away, red flag, this is not linear, but as I keep going, I go up by those changing numbers. So that's my first difference right there, but it didn't really do me a whole heck of a lot of good. I need to figure out something else. Okay, but now if I subtract these numbers, or think about what I need to add to get from one to the other, whatever your brain likes better, that's adding 2, that's adding 2, that's adding 2. Oh, hey, wait a minute. Now my second difference is now constant. And so what that means for us is that now, well, if I have a second difference, that basically means second power. So basically what we have here is a quadratic. So I'm going to have to come up with an n squared sort of thing to generate these terms. So, okay, it does take a little bit of trial and error, but start playing around and see what you can do. And a sub n, okay, I know I need something squared. So again, I need to generate myself a 7 to start with. Okay, now this, unfortunately, I can't just put down this 7 because sometimes I have to work in, or somehow I need to work in an n squared. So quite honestly, I'm just going to put the n squared. Believe it or not, that's a 2. Okay, now at this point, well, n squared, well, if I start with 1 again, I'm dealing with a 1 right there. So 1 squared equals 1, and I need to get myself to a 7. Well, maybe I'm adding 6. So let's tentatively put a plus 6 here. Alright, and then let's just test it for a couple. Alright, again, if I put in a 2, 2 squared is 4, 4 plus 6 gives me a 10. Feeling pretty good there. Okay, put in a 3, 3 squared is 9, 9 plus 6 is a 15. Alright, feeling pretty good about life in general. Just one last one, 4 squared is 16, plus 6, sure enough, is 22. So I am just completely ecstatic like Jafar. And we've got ourselves a good formula that would then generate, again, any of those terms we wanted. Or again, if I just continue this pattern forever and said, hey, what's the 375th? Well, instead of trying to continue that pattern, I could just plug in right there. Okay, moving on to recursively defined sequences. Okay, now that sounds super fancy, but it's just a sequence that generates the next term based on the previous term. And you're going to be giving the starting term and a way to get a subsequent term. Hopefully that makes a little bit of sense, but here we go. Alright. Okay, I want to write the first 5 terms of this recursively defined sequence. And I've got a sub 1 equals 5. Well, hey, I know what the first term is now. It's 5. And then ak plus 1 equals 3ak minus 2. Holy cow, what does that mean? Okay, but basically the ak plus 1, that's just a way of saying the next one. So whatever one I'm on, the k plus 1 is the next. So again, if this k was 3, then k plus 1 is the 4. So again, right there, if that's the third, that's the fourth. Okay, but here we go. The next one is just 3 times the previous minus 2. And so that's basically how it's going to go. And again, that may not make sense yet, but let's write it out and see how it goes. So a sub 1 equals, I'm going to give myself a little space, equals 5. Okay, and then a sub 2, okay, the next one, like I said, so I want the next guy, I can take 3 times the previous minus 2. Again, that's all that notation means. So 3 times the previous one, so that 5 goes right there, minus 2, and 15 minus 2 is 13. Okay, moving on, a sub 3, okay, and 3 times the previous guy. There's the 13 minus 2, and it's 39 minus 2, and that's 37. Okay, notice these guys are getting kind of big kind of fast, and that's because of the pattern. Oops, that's an a, not a 3. A sub 4 is 3 times, put that 37 in there. Alright, and if we do that, minus 2, that's going to give me a 109. And yep, getting out of control here, but hopefully haven't lost you. Okay, again, put the previous guy in there. 3 times 109 minus 2 is going to give me a 325. Okay, so just to have a nice clean answer here, the first 5 terms are 5, 13, 37, 109, and 325. Okay, hopefully that made sense. Okay, so another one, and I'm just doing this one just because there's a kind of tagged on version of something else that the book didn't want you to do here with this, and I think it's a valid thing to do, so here we go. Alright, so a sub 1 equals 3, negative 3. Alright, now a sub 2. Okay, so again, basically here I just got to take the previous guy plus 5, so this is a simpler pattern of sorts. So my previous guy is negative 3 plus 5, pretty sure that's 2. A sub 3, okay, again, previous one now is 2 plus 5, that gives me a 7. A sub 4, notice the pattern, I'm simply adding 5, so this will give me a 12, and then a sub 5 gives me a 17. Okay, so there's my first 5 terms. Alrighty. Okay, but now I want to write the general term using a sub n format from the beginning. So basically now it's just taking this recursive thing, which admittedly some people think looks very confusing, and that may be you as well. But maybe I can take this and turn it into something that looks more like a y equals mx plus b sort of thing, and again with a simple plus 5 each time, that should be doable. Alright, so again my nth term, and again because this is a relatively simple one, I can get kind of my start, and then what am I doing to it? Well, I'm adding 5, and again I'm adding it n times, but I'm always doing 1 less, because again on the first one I certainly didn't add anything to the negative 3. So again, there's my basic format that I like to go with. And again, a little bit of simplification, 5n minus 5, combining like terms, gives me a nice pretty 5n minus 8. And again, if you don't believe me, feel free to check in any value of n for that, and it should match up with the ones that we generated here. Okay, now changing gears a little bit, we've got factorials. Now I love factorials because it makes it look like you're super excited about numbers. You may have been exposed to these before, but if not, here's the full explanation for you. Okay, factorial, okay, this only works with whole numbers, and this exclamation point, again, is not you being excited about a number, but it's fun to say 5! But anyway, that's not really what we're going after. Factorial means you're taking every number, starting with this number, again, whole numbers, counting down to 1, and then you're going to multiply them all together. So basically 5 factorial means 5 times 4 times 3 times 2 times 1. I admit including the 1 is a little bit silly because of course 1 times anything won't change anything. But if I multiply all these guys together, it gets me a 120. Okay, you can probably find the factorial symbol under a numbers probability menu someplace on your calculator. So take a couple seconds someplace and look around for that. Okay, one thing that's quirky about factorials is 0 factorial. Well, again, the definition I just said, you just go down to 1, and well, hey, he's below 1, so that doesn't make sense. But because of the way some formulas and stuff use factorials, basically 0 factorial is 1, and that's 100% by definition. And quite honestly, it's mostly so that some formulas that involve factorials don't fall apart in certain situations. So by defining that to be 1, all those formulas work out just fine. Okay, moving right along. Okay, if I have n factorial, okay, well obviously that doesn't make a whole lot of sense unless you know what n is, but again we can represent this symbolically just by starting with n, and then of course, well, what's 1 below n? Well, that's n minus 1. What's 1 below that? That's n minus 2. And then we can continue that forever, and again, granted I don't know exactly where I started, but wherever I started, I'll go down to 3, 2, and 1, and get to the end. So that's what n factorial would look like if you had to write it out not knowing what n was to start with. Now granted, it could have been a 1, or it could have been an 8 million. You just don't know. Alright, now it is possible to simplify factorials without a calculator, and I'll admit, depending on the numbers. I mean, with certain number combinations, this might be just ridiculously long amount of work, but depending on the numbers, it might be a pretty simple thing to do. Okay, for instance, 12 factorial simply means 12 times 11 times 10 times 9, etc. Okay, so I'll just kind of do that for now, using a little bit of proper, or improper probably, shorthand. Again, notice the 9 factorial. That's just simply 9 times 8 times 7 times dot dot dot. Well, hopefully you can look at that and go, wait a minute, there's a whole bunch of stuff that matches, right? This 9 would cancel that 9, the 8 would cancel the 8, the 7 would cancel the 7, and the 6's, 5, 4, 3, 2, 1's would all cancel. So really, 12 factorial over 9 factorial could probably better be written as 12 times 11 times 10 times 9 factorial, simply over 9 factorial, and you just have the 9 factorials cancel. Okay, and then 12 times 11 times 10, okay, well, if you're a good third grader, you can do that in your head, because 12 times 11 is 132, and then anything times 10, you just tack a 0 onto it. So that's 1,320. And that's how you can do those without a calculator. Again, depending on the numbers. If it was 52 factorial over 3 factorial, well, then that's going to be pretty tough. But if these numbers are pretty close together, it actually comes out pretty easily. Alrighty, now what happens if you've got variables? Okay, I think the most important thing if you're trying to simplify an expression with factorials with variables intermixed in them is mostly identify who's bigger. Okay? Well, obviously n plus 2 factorial, well, or just better yet, n plus 2 is bigger than n. So all I really need to do is take my bigger one, in this case the n plus 2 factorial, take him, start counting down. Well, of course, n plus 2 minus 1 is n plus 1. And then n plus 1 minus 1 is just n, which, hey, that's what I have on the bottom, so I'll stop right there, n factorial. And then again, there's my n factorial, which cancels out. And then basically just have n plus 2 times n plus 1, which, admittedly, that one, that's pretty small, so we should be able to FOIL that one pretty nicely into n squared plus 3n plus 2. And there you go. So then any for value of n, you wouldn't have to work out this whole thing. You could just work out a simple polynomial instead of these two big factorials. Alright, that being said, the second one tends to mess people up, because since the first one, this guy that looks bigger, you broke that one up, people start breaking up this. But if I asked you what's 1 less than 4n minus 1, hopefully you don't tell me 4n. You tell me 4n minus 2. So basically, because this guy is the bigger one, he's the one I want to mess with. Okay, so I've got 4n, and then of course 1 less than that is now 4n minus 1, and since again that's what I'm looking at on top, that's where I can stop. So 4n minus 1 on top as well. Of course, this guy cancels with this, and basically that just gives you 1 over 4n. Okay, again, the number one mistake there is people start breaking up this one into 4n minus 2, 4n minus 3, 4n minus 4, etc., but you never run into 4n that way. So be careful. Or, again, the flip side is they break this guy up and say that 1 less than 4n minus 1 is just 4n, which is equally wrong. So this is the way to handle it. Okay, anyway, I've babbled long enough, so of course, hopefully that all made sense. Again, if not, please ask me in class for any questions that you have.